Right, last time we said that an isomorphism between covering spaces is a homeomorphism that intertwines the maps, right? So that is to say, that fits into this diagram and makes a commute. Right? This induces an equivalence relation between, equivalence relation on covering spaces. And we saw that the equivalence classes are determined by the image of the fundamental group under the induced map, the induced homomorphism. Or up to conjugacy if, as in this diagram, you don't keep track of base points. Then given a covering, we saw that there is an induced action of the fundamental group on the fiber. Right? So elements of here are represented by loops down here, but as we know, you can lift a loop and then it becomes a path, right, that might do something more interesting up here. And so in particular, it does, it gives you an action of the fiber. It gives you a bijection. Right? In fact, this is a homomorphism between the fundamental group and the symmetries. Okay, then the self-isomorphisms of a covering make up a group. The group of deck transformations. Right, which we sometimes write G of x tilde, or if we want to put everything in, deck of x tilde to x. And if x tilde is path connected, x is path connected and locally path connected, then we computed that this is equal to a quotient by the image subgroup, right? So you take the normalizer and mod out by the image, and that gives you the deck transformations. So this is particularly nice if H is a normal, so if x tilde to x is a normal cover, right, which we defined as saying that the action is transitive. Right, so we defined it in this geometric way. We said that given any 2 points on the fiber, you can find a deck transformation that takes one of them to the other. Right, but we proved that that's equivalent to an algebraic condition, namely that H is normal in the fundamental group, right? Which of course is what's relevant over here, because it tells you that up here you can put the whole fundamental group, right? So in particular, this is nicest if you have a universal cover. Then the deck transformations coincide with the fundamental group. Okay? That's what we did last time. Questions on last time? Okay, wonderful. So the first thing we want to do today is think a little more about this, about having a covering space and the set of deck transformations acting on the total space, on the upstairs, right? So you can think that the downstairs is exactly what you get by looking at the things upstairs that are connected by deck transformations, right? So you could turn this around, and instead of starting with a covering and then looking at the deck transformations, you could start with a space and a group acting on it and see if you can then construct a covering from that. Okay, so some vocabulary for that. Let's say you're given a group in a space Y, an action of G on Y is a homomorphism from G into the homeomorphisms of Y. Okay, so this is what we want, because we're just thinking of the group as an algebraic thing, no topology on it. If we wanted to include some topology on it, you could ask that the map, where you take an element of the group, an element of the space, and then look at the action, you could ask that this is continuous. Right, but if we're not putting a topology on the space, or equivalently, if we're thinking of the group with the discrete topology, then there's nothing to check. Right, just that you get a homeomorphism on Y. When a group acts on a space, we denote it like this. We put G and then a round arrow on Y, right, to show that G is acting on Y. And as I already did here, we usually abbreviate. Instead of writing rho of G acting on Y, we just put G dot Y or G times Y if we are feeling lazy. Okay, so an action is faithful. Right, so I'm going to give you a couple vocabulary words just for general culture. You should know these words. But actually, we don't care about them. We're going to use the third property that I'll list. But it's good to know. An action is faithful if rho is injective. Right. This is also called effective, so known as effective. Okay, so this is saying that the different elements of the group give you different homeomorphisms, right? So no two elements act exactly the same way. The most important property you see for a group action usually is whether or not it's free. So an action is free if every rho of G is an injective homeomorphism. Okay, so notice effective means that rho is injective, right? So, so no two elements give you the same homeomorphism. This tells you that each one of them is an injective map, right? So in particular, if an element in particular free says that if g times y is equal to y for any y, for some y, then g has to be the identity. Well,
What do you mean it's always injective? It's a homomorphism. You mean to say
without fixed points.
okay, the rho G doesn't have
Fixed points.
no, not when that.
You're right, it's a homeomorphism. So
rho G, no rho G has a fixed point besides the identity.
no rho g has a fixed point despite, yes, exactly. Yes, maybe I didn't want to say, no, I definitely wanted to say homeomorphism because you have an inverse, right? You just act by the inverse element and that undoes it.
Yeah, so it's a group, so of course they are inverses.
Yes.
By definition, it's a homomorphism.
Yes, so what am I saying wrong?
Just delete injective, everything else is fine.
Well,
If
yeah, so this is certainly true, but I'm,
if no rho G has a fixed point.
if this, yes, but I'm confused about why. But anyway, this is what it means to be free. Thank you. Okay, the one we actually will care about. Well, no, I should give you one more. So proper. If the map where you look at the action of the group on the space and how far that takes you from where you started is a proper map. All right, and remember, proper maps are continuous maps that whose inverse image of a compact set is compact. Right? So any continuous map sends compact sets to compact sets, right? But doesn't necessarily pull back compact sets to compact sets. Right? For example, the constant map on the real line. The inverse image of a compact set need not be compact. But we call it proper if the inverse image of a compact set is compact.
Can you say that one more time?
Yeah. So any continuous map will send a compact set to a compact set, but not necessarily pull back compact set to compact set, right? And so the example of a constant from a non-compact space is an example of where that doesn't work. We say that it's proper if it does work, if the inverse image of a compact set is compact. Okay. So again, this is really relevant if G is a topological space, right? Otherwise, you don't have to worry about topology, and you just think of G as being a discrete set. Okay, so the property we actually care about. Yes.
So in the definition of proper, by X, do you mean Y? Because I think you Y.
Yeah, that's what I mean. Thank you. Okay, so here's the one we actually care about. An action is a covering space action. If every y has a neighborhood U such that all of the images G of U, G and G are disjoint. Right? Another way of saying that is that if you have G1 intersect G2 of U not empty, then G1 is equal to G2. Okay, so this implies free. And if you like, this says that orbits don't accumulate. All right, of course, the orbit of y is just the images. Right, what you would denote like that. Right, so the orbit is just what the image of y under the action, and this tells you that the orbits do not accumulate. Okay, so in other textbooks, what the actions you care about are called is a terrible name. It's properly discontinuous. And so I think the name comes from you're asking for a proper action, but you're thinking of the group as being discontinuous, so having the discrete topology. So I think that's where the term comes from. Much better, as in Hatcher, to talk about covering space actions. So just this. Much.
A deck transformation would be covering space action.
That's right. So yes, we will see in a few seconds that that's true. Yes. But yes, that's why. And in fact, we'll see conversely that if you have a covering space action, you can construct a covering space.
So are these actions proper?
They are. They're proper with the discrete topology. So they are properly discontinuous. But what's unfortunate is sometimes properly discontinuous is defined just like this, but you only ask that this be, you allow finitely many intersections. Right? So that's why it's a confusing term to top it off. Okay, very good. More questions on this? Okay. So yes, let's check that indeed deck transformations act, the deck transformation group acts with a covering space action. So note, G of x tilde acts on x tilde is a covering space action. So, as you'd expect, all you do is, given a point in x tilde, pick a neighborhood. That projects homeomorphically along P, right? So, i.e., P from u tilde to P of u tilde is a homeomorphism. Okay, then if you have a non-empty intersection, then you must have points in u tilde that have the same image under these, but then P of G1 x1 tilde is equal to P of x1 tilde, which is the same as P of G2 x2 tilde, P of x2 tilde, and that tells us that x1 tilde is equal to x2 tilde, right? But then we have deck transformations, and they coincide at a point, so they coincide everywhere. Yes,
Are G1 and G2 elements in the deck transformation?
that's right.
Okay.
Yeah.
How are you getting that P of G1 x1 tilde is equal to P of x1 tilde?
Because G1 is a deck transformation. So it it preserves the fibers of P,
Oh, okay.
right? So, yes, I've erased the diagram, but yeah, G1 sits in. All right, G1 makes this commute. Okay, so deck transformations are examples of groups that act with the covering space action. So now we'll start with a group that acts with the covering space action. We'll construct the covering space, right? We talked about the orbits there. I want to say that the orbit, being in the same orbit, gives you an equivalence relation. So a group action induces an equivalence relation with y1 is equivalent to y2 if and only if there exists an element of the group such that y2 is G acting on y1. Right? Because the group action is a homomorphism into the homeomorphisms, this is an equivalence relation, right? So you have symmetry and transitivity and so on. So the space of equivalence classes is denoted Y mod out by G and called the orbit space. Right, as usual, we endow it with the quotient topology. Okay, so here's the proposition. Let's say that G acts on Y by a covering space action. Then, okay, the quotient map is a covering space. If Y is path connected, then the deck transformations coincide with G, with the action of G. And if Y is also locally path connected, then G is isomorphic to the fundamental group of the quotient mod out by the image of the fundamental group of Y. This, of course, follows from part A and what we did last time. Okay. Great, so we want to prove that this is a covering space. So as usual, we want to find a nice cover down here of evenly covered sets. Well, perhaps right before I erase that, I will use it. To prove, let's use this. So given U such that G of U with G and G are disjoint, okay. P identifies, well, let's say like this. P G of U is it's the same for all elements of G. So the image is the same in this quotient space, right? Because things are identified in this quotient space if they differ by the action of the group, right? So, and clearly we're just acting by the group, so you get the same set. By definition of the quotient topology, P restricts to a homeomorphism between U and P of U. So we have a covering space. Right? Yes?
So, for your first statement, why do we need the G of U to be disjoint for that to hold?
Well, I want to get a covering space, right? So I want things to be evenly covered.
Oh, okay.
Right,
So
so-
you're not saying if they're disjoint, then P of G1 of U is P of G2 of U.
That's correct.
You're just
This
saying
is,
these are both
right, this is going to be
parts of
true. Yeah, exactly. This is always going to be true because P doesn't care about what you do with G, right? But because these are disjoint, I now have an evenly covered neighborhood downstairs.
And presumably, we also use the fact that the quotient map is surjective.
Sure, although if you look back, a covering space map for Hatcher does not need to be surjective.
Oops. That's right.
Yeah, but in this case it is surjective. Yes. Okay, so G clearly acts by covering transformations. And the covering is normal. Since if you act by G2 times G1 inverse, this takes G1 of U to G2 of U, right? So remember that whether or not a covering is normal, we have two ways of checking. You can check geometrically or you can check algebraically, right? Geometrically, what you need to check is that every 2 points on the fiber can be connected by a deck transformation, right? So it's easy here because 2 points on the fiber above U, well, in fact, the whole neighborhood is taken to this neighborhood by this element. Right. Okay. So, so far we have the G as a subgroup of the deck transformations. Okay, so now assume that Y is path connected. and you pick an element of the deck transformations. Okay, pick a point in y. Note that f of y, equivalence class, yeah. So. Right, so because you have a deck transformation, you know that wherever it is that f of y lands, it's somewhere in the same fiber as y. Okay. But because they're in the same fiber, and we know that the action of G takes any point on a fiber to any point on the fiber, there is an element in G such that G of y is this f of y. Right? Okay, so the action of G is by deck transformations. So here we have two deck transformations, and their image coincides on a point. So because we have path connectedness, deck transformations are determined by what they do to a single point, and so they coincide everywhere. G of y is equal to f of y for every y and y. Okay, so that gives us parts A and B. And then, as I mentioned, part C follows immediately from what we did before. You know it's a normal covering, so you can put the fundamental group there instead of the normalizer. Okay, so the point is that sometimes it's much easier to construct a cover by coming up with a group action that has the covering space property, as opposed to staring at the maps and constructing a cover by hand, say, that is evenly covered. Right? So let's do an example. Okay. So we're going to build in the group action. So let's start by drawing a pentagon. It's supposed to be regular, but close enough. And then we're going to draw like a starfish with one tentacle towards each vertex. Again, supposed to be regular, but whatever. And then we'll put one hole right in the center, and then some number of holes along the tentacle, same number. And again, it's supposed to be symmetric. Okay, so this has symmetry by construction of rotating by 1/5 of the circle. And by flipping would also work, yes, but I don't want to do that. I just want to rotate, right? Okay, and if you look at these circles, these loops, they would get identified by this rotation, right? So we're going the orbit space. So C mod 5C ax, and the orbit space looks like the other way around. A surface with 3 holes, where these two got identified, closing this up, if you like. Right? So you can think that each one of these tentacles, you think of it by itself, and it has these two circles, but those two circles need to get identified when you take the quotient, and so they close up and form this third whole.
Can you explain that again?
Yeah. So think of each. So if I want to see what the orbit space looks like, it's enough to take one of these tentacles, right? Because then every orbit is represented somewhere in this tentacle. But when I take this tentacle, I have these two circles, right? So it would look like something like this, and then a circle, and then a circle, and something like that.
Where are those two circles coming from?
I drew them in. So yeah, they were just distinguished loops inside. They're not, part of the structure. That's right.
Okay.
Yeah, they're just things we're looking at.
Okay.
And but under this action, this rotating, they get identified with each other. So you can think that this one gets longer and longer, like that, and this one gets longer and longer, and you identify them, and you'd end up with a hole in between.
Poor starfish.
Yes. Okay, but it's easy to see that this is a covering space action, right? Because all we need is that every point has a neighborhood so that it's disjoint from all of the images, right? But just take a point in the neighborhood and the images stay on different tentacles, and so they're all disjoint. Right? So it is a covering space action. This is covering space action. So we have a cover. This gives us a cover from the oriented surface, or orientable surface of genus. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 to the oriented surface of genus 3. All right, so we could denote that, say, M11 to M3. Okay, but of course the construction generalizes trivially, right? Just take any regular n-gon to start, right? So same construction. Start with a regular n-gon, and then on each tentacle, not a technical term, put m holes, right? And then you end up with a covering of nm plus 1 to m plus 1.
What would have happened if you didn't have that hole in the middle?
I would have some point that's being fixed by the action,
Okay.
right? And I can't have that. Okay, so later you can use an argument with the Euler characteristic to see that if there is a cover between orientable surfaces, the genera are related in this way. right? So if you have a covering between orientable surfaces, say m sub g to m sub h, then g has to be a number of this form and h a corresponding number of this form. Okay. So I mentioned the Euler characteristics of the first class when we were talking about the history of topology. So it's vertices minus edges plus faces, and then you keep going with this alternating count as the dimension goes up. So in this case, what you would do is you would triangulate your surfaces so that you have some combinatorial structure and it looks like just vertices, edges, and faces. And then you count this alternating way. And it turns out that the number you get is a topological invariant. And it behaves very nicely with respect to covers. And so you can use it to figure out the genera. My favorite way of seeing that it behaves very nicely with respect to covers is that you can prove that it is given by the integral of an appropriate differential form. And then you could just pull up that differential form, and then you're just integrating upstairs the same form you were integrating downstairs. So it just gets multiplied by the number of floors. But anyway. Yes?
So if we were to look at the subgroup of the cover, or of the fundamental group of the three-hole torus induced by this,
Yes.
would we get like the subgroup generated by x, y, and z to the fifth?
Would you get...
If x, y, and z are the generators. No, wait, never mind.
No, you would not.
I am
Yeah.
completely confusing two different things.
Mm-hmm.
So for this example that we just did, we like kind of went from the covering space to the thing that it was covering.
Yes.
Would you ever notice how you said that we could use group actions to go the other? I thought you said we could use group actions to go the other way.
That's right, but this was going the other way. So the two ways are you can start with a covering space, and then you have a group of deck transformations, right? So you started with a cover, and then you went to what group is acting upstairs to give you the space downstairs.
Okay.
And here we went the other way. We started out with the space that was going to be upstairs and the group.
Okay.
And then we used that to figure out what the space downstairs was.
I'm asking, can you start from downstairs?
Can you start from downstairs?
With the cover?
So we've sort of done that before, because what we showed was that you give me a space, a well-behaved space, and any subgroup of the fundamental group, and there is a cover, right, that does that. So the answer is yes, but it's something we've already done. And we've done it in a couple of different ways, because you could also start with the space downstairs and the fiber and the action you want to have on the fiber. And then we saw that for well-behaved spaces, determines a covering. Okay, more questions?
Are there other actions besides symmetry that we might notice to get a...
Well, in some sense, the actions are symmetries. Right? In fact, you could think of group actions as a thing, as just a way of generalizing symmetry, the notion of symmetry. Right? So what does it mean that a space is symmetric? It means that there is some group that acts on it without changing it. Right? And so, so then you can define different parts of geometry by what sort of symmetries am I allowed.
And then, last question.
Sure.
What Nick was asking about the flipping symmetry?
Yes.
What would that do?
Well, it would leave fixed the things, the axis, right, where we were flipping. And so that would be unfortunate for thinking of a covering space.
Well, I mean, the way you fixed the fact that the middle would be a fixed point is you put a hole there. Could you, like...
That's true.
somehow-
I'm not seeing it.
Okay.
Yeah, you'd want a whole like
Right.
ray or something, or plane. Yeah, no,
Okay.
yeah.
You might be able to like essentially poke a hole through it and then rotate around the third axis to do the flipping, in a sense.
Well, even
It's not
so,
quite the
if
same
there
as a
are,
reflection, but
right. Yes, but that's not what I'm doing. I'm just rotating. Yes.
if it was a hexagon instead of?
Well, the problem with any reflection is going to be, the problem with anything you try is, do you leave anything fixed, right? Because we have this covering space property that we need to preserve, right? So it says there are no fixed points, and it says that in a strong way, and that there are whole neighborhoods that don't intersect. All right, so that's the thing you have to watch out for when you're cooking up your group. More questions? Okay. So, as an easy corollary, if Y is simply connected, and we have a covering space action by some group G, then the fundamental group of the orbit space is G. Right, because G is the universal cover of this space, and G is the group of deck transformations. So this actually shows up a lot later in geometry. It turns out that if you have a group given, I think it works for any topological group, there is a contractible space denoted EG on which G acts freely. I think it's a covering space action. I think. But then BG is what you call the orbit space, and this is called the classifying space of the group G. So yeah, when you're doing topology and you want to study things equivariantly, so you want to have a space that has a group action, and then you want to study, say, the fundamental group or homology groups or all of these invariants. You want to study them equivariantly, so you want to keep in mind the group action. Then often what you do is just multiply the space by EG, because topologically this is contractible, so who cares, right? But now you have a free action on G, and so now your space is very well behaved with respect to the group action, and no worse behaved with respect to topology.
What do you mean multiply by EG?
Just Cartesian product.
Okay.
Take your space and cross it with EG. Yeah. So topologically, that's a great thing to do. Analytically, it's a terrible thing to do because these spaces are always horrible and almost always infinite dimensional. And so you've taken what could have been a very nice space and messed it up. But that's used a lot. OK, so questions on covering spaces, covering space actions?
Could you maybe see an example of the corollary?
Sure. So the simplest one would be just think of y as r, g as the integers acting by translation.
And this gives us S1 back.
Exactly, yeah. So what you have is every orbit is represented by, say, somebody in the unit interval. The endpoints get identified, and so your orbit space is S1.
So basically, this is the same thing we said earlier, but backwards. Namely, when we said earlier that if you have a simply connected covering space for some space, then the group of deck transformations is the fundamental group of the space on the bottom.
Yes.
This is just the same thing.
This is the same
viewed from
thing,
the
but
perspective of the top.
exactly. You start out upstairs. Yeah.
Okay.
Yeah. Okay, more questions on covering spaces.
So this is from a while back.
Sure.
There's a map P star induced by P, and it's a homomorphism of fundamental groups.
Yes,
When is it injective?
it's always injective.
It's always injective.
Yes,
Cool. That's what I thought, but
yes.
just wanted to make sure.
Okay. More questions? Yes.
So I guess then that would imply that the fundamental group of the 11-hold torus can be realized then as a subgroup of the fundamental group of the 3-hold torus.
That's right. Yes.
It's
Yes,
a
and
little counterintuitive, but I guess
it
the
is.
same thing happens with graphs.
That's
so-
right. That's right. And that's where it's really counterintuitive. Yeah. That the free group on 2 generators contains the free group on 3 generators. That just doesn't make any sense. Yeah. Yes.
Is this where the return will come in? Like,
That's right. So that's the end of chapter 1. Yes. Okay. Perfect. So indeed, that is the end of chapter 1. So it's worth taking a moment to think about what's wrong with pi 1, right? So why is there a chapter 2, right? So pi 1 is great. It does its thing very well. But for example, we want to distinguish Sn from, say, S2 if n is greater than 2, right? Because at the moment we can distinguish S1, but all of the higher Sn's are simply connected. And so pi 1 doesn't notice any difference. We want to get beyond the 2 skeleton of a cellular complex. Right? So we saw that the fundamental group of a cellular complex is the same as the fundamental group of its 2 skeleton. Right? And it's generated by the 1 skeleton. Okay, so the first thing you might think of is to do higher homotopy groups. So think of pi n of x with some base point as homotopy classes of maps from the n-dimensional cube to x that send all of the boundary to the point x naught. Right? So that's just ramp up the dimension of what we've done. This is the same as homotopy classes of maps from the n-dimensional sphere with some base point to x. So homotopy classes of pairs. The operation is not hard to describe. So here's what we did for S1. You have a circle, and you pinch it to form 2 circles, and then you map the top circle using F and the bottom circle using G, and this composition was doing F followed by G. Right? So that's pictorially what we did to get from 2 loops in G a single loop in G, where you just do F and then G. Right? So, well, we can draw the same picture in higher dimensions. Right? We just make it look 3D. Right? And you're doing the same thing. You're just taking this equator and smashing it to a point, right? And then just defining the operation like that. So defining higher homotopy groups and getting groups is not difficult. You did a problem on the homework where you had to show that pi1 of x times y is isomorphic to pi1 of x times pi1 of y directly. So you had to construct a homotopy showing that elements commuted. Right? So it turns out that same argument, depending on how you did it, but possibly that same argument is what you use to show that higher homotopy groups are commutative, always. So for higher n, you always get a commutative group. So you could think, well, that's wonderful. Why is it that that's not what we're studying next? And the problem is that although these are really easy to define, they are hard to compute. And like the intuition is a bit tricky too. So for example, if you just look at the 2-sphere, then we've seen that pi1 is trivial. Pi2 is very reassuringly the integers, right? Just like pi1 of S1. So again, it's just like a degree. How many times do you wrap the sphere around the sphere? And it's certainly noticing the two-dimensional whole, right? As it should. Pi2 should be counting two-dimensional holes, right? So here's what's wrong. Pi3 of S2 is also Z. Yeah, so there are three-dimensional holes in the two-dimensional sphere. This is generated by the Hopf vibration. If you've heard of that, and if you have not heard of that, you should definitely go check out YouTube videos of the Hopf vibration. And then, for example, pi4 is C2, pi5 is Z2, pi6 is C mod 12. So they're hard to compute and they're hard to understand. They're not counting what we would hope they would count, right? They're not counting, or another way of thinking about it is, well, there's this three-dimensional hole that I did not know was there. That's not what I was looking for. Okay. You could also
the notion of homotopy no longer counts holes the way we want. We understand what holes should be.
That's right. Yeah.
It counts something else.
It counts something else. That's right. Yes. So one problem that is fixed just by being abelian is that with pi1, it's sometimes hard to distinguish the groups you get. So we saw, for example, that if you compute the fundamental group of the torus, you get a presentation like that using well, Van Kampen, for example. And if you compute the fundamental group of the two-hole torus, you get a presentation like this: A inverse, B inverse, C, D, C inverse, D inverse. Right? And so while those don't look the same, right, they're just finally presented groups. How do you show that they're not the same? Right? In this case, we had a nice trick, which was to look at the abelianization. Right? So let's abelianize. And there you can see that they're different. Okay, so So that's just a feature of having abelian groups. So what we're going to study next, which is homology, is going to fix these problems, right? It'll have its own problems, but it'll fix these problems, right? It will, if you have an n-dimensional manifold, the homology will stop counting at dimension n, and it'll be abelian groups. So, so in principle, it's easy to distinguish whether you have the same group or not. And this, again, we mentioned the first class when we were talking about the history. This is going to be n-dimensional things without boundary sitting inside X, where you mod out by boundaries of n plus 1 dimensional things. And yeah, the problem is, well, what do we mean by things, right? So, and I mentioned Poincaré's initial attempt was to use manifolds, and that did not work well. So we'll do something that does work well. The theory was started by Poincaré, but it was really Emmy Noether who noticed that what you really should be thinking about are these groups. Poincaré was focused just on their ranks. And you should focus on these groups. And then every time you have a map between spaces, you end up with a homomorphism between groups and so on. OK, so what I want to do today is just try to give you the idea of what homology is going to be like. And then after the exam, we'll write down some formal definitions and start trying to compute. Right? So let's start just with the first couple of groups are really easy. H0 of x is just going to be c raised to the number of path components of x. OK? So this one's easy because what's supposed to be is zero-dimensional things without boundary, but zero-dimensional things just don't have boundary. Right? Mod out by boundaries of one-dimensional things. So if your space X looks like, say, a couple of copies of the torus, then a typical element of the top, zero-dimensional things, is just a bunch of points. Right? Whereas the boundary of a one-dimensional thing is, well, take a path and then look at the boundary. Right? Now, when you take the boundary of a path, so let's say that this is the point x0 and this is the point x1, and this is the path gamma, then the boundary of gamma is going to be, well, I'm going to put an orientation, and then I'm going to take x1 minus x0. So I'm going to allow points to have a sign. So the way we want to do that is, well, here, the zero-dimensional things, really think about the free abelian group generated by zero-dimensional things. So to every point, I allow a coefficient, right, given by an integer. So then I'm OK with subtracting points, right, because I'm subtracting within this group where I'm allowing the points to have coefficients. Right? So really here I would have C0 equal to free abelian group on the points. C1 would...
By boundary, you don't mean boundary, because points have boundary, namely themselves.
That's right. So I don't mean the topological boundary. I mean some boundary map that's going to take you from one-dimensional things to zero-dimensional things, zero-dimensional to minus one-dimensional things, which is just empty, and so on. Free abelian on paths, say. And then I have a map from C1 to C0 that takes a path, takes gamma to x1 minus x0. Right? And now it makes sense because the free abelian group on points, I allow points to have coefficients. Right? And then you can see that you are going to get z to the number of path components. Right? Because when are 2 points going to be equivalent? Well, 2 points are equivalent if there is a path joining them. Right? Because then they appear as a boundary. The difference appears as a boundary. Right? OK. Okay, well, what's h1? h1 is going to be just pi1 of x abelianized. Well, I'll just leave it easy. All right. So C2 would be like free abelian group on, well, let's say 2 cells if we're in a cellular complex. So then H1 would be, paths without boundary, right, which is loops. And then you mod out by the boundaries of 2 cells, right? So if I have some path here and some path here, then I have a perfectly good element of C1, so in C1. So in C1, well, because I'm taking the free abelian group, right, so it's abelian. So I don't care if you do E1 and then go back on E2 or go back on E2 and then E1 or whatever. It's abelian. So I would just take some multiple of E1 plus some multiple of E2. Right? So and then my relations are going to be whenever I have something filled in, right? So if we have this filled in, call that A, 2. So I'd want to orient it somehow. So if I think of it as a 2-cell, 2-cell has an attaching map, right? The attaching map is some way of gluing that in, right? So you would glue it in like that, say. Then the boundary of A would be go along E1 and come back along E2. Okay, and so you can see that we're really getting just loops mod out by boundaries of 2 cells. So of course, this boundary of the 2-cell, you can think of this as just giving you space to homotope from E1 to E2, right? But here, it has the same effect that in this group, you're identifying E1 and E2 when you take this quotient.
I see. So the natural thing from going to from S1 wasn't S2, but you just had to fill in the hole as opposed to like.
That's right. Yeah, exactly. So just fill in the inside. Yeah. So for example, let's say that x is, let's take the same graph. So let's put E1 out here this time, E2 and E3. Let's make this point x1, this point x0. So here, C1 would be the free abelian group on, no, C0, say, on x0 and x1. C1 would be the free abelian group on E1, E2, E3. So H0, right, is just Z to the number of path components. It's a path connected space, which is Z. H1 would be this free abelian, let's look at H1. The boundary of E1 is x1 minus x0. And that's also the boundary of E2 and the boundary of E3. Right? So if I want something in C1 that doesn't have any boundary, right? So the boundary of an arbitrary element here, so say A1, E1, A2, E2, A3, E3, is, well, I'm definitely going to make the boundary map linear over Z. So this is just going to be A1 plus A2 plus A3 times x1 minus x0. right? So the only way you get 0 boundary is if the coefficients add up to 0. Right? So one-dimensional things without boundary, that is A1 E1 plus A2 E2 A3 E3 such that A1 plus A2 plus A3 is equal to 0. So H1 of x is equal to just this because I don't have any two-dimensional pieces to mod out by. Right? And of course, if you have A1, A2, A3 with this relation, so you have z to the third, but with one linear relation, that's just z squared. Right? Because, for example, I can determine A3 from A1 and A2. So let's throw in a two-dimensional piece. Let's throw in A here with attaching map that goes like that. So C2 is now the free abelian group on A. The boundary of A is E2 minus E1, right? So there's the only thing in here, if you do n times A, you get n times E2 minus E1. The only way that's 0 is if n is 0, right? So H2 here would not change at all, right? This would still be 0, because I don't have any two-dimensional things that don't have boundary. Right? All of my two-dimensional things have boundary. On the other hand, H1 would change. So the one-dimensional things without boundary, that's still going to be A1, E1 plus A2, E2, A3, E3. But now, if I mod out by the boundaries of two-dimensional things, I have to mod out by this E2 minus E1. Right? So I would mod out by n times E2 minus E1, well, for all n. Okay, so this just tells me that, well, E2 and E1 are giving you the same element. And then since the coefficients are still adding up to 0, then I only need one coefficient. Right? So I just get z. Right? And of course, this space, you would think, well, homotopically, this is just a circle. Right? And so a circle, H1 should give you z. Right? It's just pi1 abelianized. Let's just complicate it a little bit more. What if you attach another 2-cell using the same attaching map? So let's take x double prime. So we're going to have E1, E2, E3. And then here we're going to attach A and B. Attach same attaching map. So what happens is that this acquires a front flap and a back flap, and so it ends up being filled in, or rather a hollow thing, with let's say A in the front and B in the back. Right. So now C2 is the free abelian group generated by A and B. The boundary of A is E2 minus E1, just like before, but now that's also the boundary of B, right? So now H2 of x double prime is all of the two-dimensional things without boundary, right? So that's NA plus MB such that M plus M is equal to 0. And I mod out by the boundaries of three-dimensional things, but I don't have any three-dimensional things. So it's just this. And of course, that's just said, right? Because if you give me n, I can tell you n. OK. So and then h1 doesn't change because the image of the boundary didn't change, and h0 doesn't change. OK, so you can see part of what's going to be difficult if you try to do this more generally is I need to know the attaching map here so that I can compute the boundary, right? I need to keep track of orientations so that I know what the boundary is, right? And so the way we're going to deal with that is we're going to use special, not just polyhedra, but very special polyhedra. We're going to use simplices, right? So the simplex, the n-dimensional simplex, is the convex hull of n+1 generic points in Rm. So we're going to use those because those we have a very simple like algebraic or combinatorial way of talking about orientations. So we're going to use those as building blocks. And then you could think, well, it's like a cell complex. You're just going to take something that's built up from simplices, not surprisingly called a simplicial space. But we're going to do much worse than that. We're going to take an arbitrary space, and we're just going to look at all maps from simplices into that space. So we're going to have these huge chain spaces, the CIs. But the quotient groups are still going to be finite dimensional and nice.